Okay, my talk is going to focus on flooding and climate change and the work that we've been doing to support climate resilient floodplain management. So I want to start with this kind of goofy schematic of a watershed just to illustrate the primary climate change impacts affecting flooding. So the first one is declining snowpack. The way that this is typically talked about in terms of a transition from snow to rain. I think in terms of flooding, it's more helpful to talk about it in terms of a change in the geometry of the watershed. As the snow line rises, there's just more surface area that rain is falling on and more potential for that rain to end up causing flooding. On the other end, we have sea level rise, a fairly straightforward effect on coastal and lower river flood risk. The main thing to know about this, similar to snowpack, is that there's past trends that have been significant, and we actually expect near-term changes to be important as well, in addition to accelerating beyond into the century. That's in contrast with heavy precipitation, where the past trends really don't show any change, and the projections really show the most change, the most notable changes in the second half of this century. So in the near term, we don't expect big changes in extreme precipitation. In the longer term, we do expect it to be an important driver of changes in flood risk. There are other factors. One is snow sediment processes. So we have deep receding snow lines exposing more dirt to erosion. We have heavier rain events. We have higher peak flows. They're going to be more erosive. All of these things are going to increase the mobilization of sediment and the risk of landslides, which could also carry sediment. At the same time, at the lower basin, you've got sea level rise pushing back on flows, slowing river velocities, which is going to increase the rate that sediment, that all of that new sediment too, is dropped into the channel, and that can actually cause the channel to become just smaller. Decrease the capacity of the channel, and increase the risk of flooding as a result. And then finally, elevated groundwater. Groundwater flooding is an issue in parts of the region, and wetter winters are going to contribute to an exacerbation of that, as well as sea level rise on coastal areas. And that's not to mention the additional issue on the coastal side of saltwater intrusion. So we've worked on all of these over the past couple of years in focusing on flooding. But I'm not going to touch on any of that work except some of the work related to heavy precipitation. So heavy precipitation. So the sort of big study coming out in this area is the one from Mike Warner's PhD thesis. And this is basically taken directly from his 2015 paper where he looked at the CMIP5 projections for what they said about the frequency and intensity of atmospheric rivers, which are by and large the way that we get heavy rain events and flooding in the region. So he found that there was a clear trend in those, this 22% increase by the end of the century. And this is significant because the work before was kind of ho-hum about precipitation change in the region. And that's because that work had really focused on seasonal and annual precipitation. There wasn't, at the time, global climate models didn't capture extremes well. There wasn't a way to look at changes in extreme precipitation. And the trends in the annual and seasonal precipitation are ho-hum. They're small relative to year variability. That turns out to not be true for extreme precipitation. So that's the important finding from Mike's work. And just one detail about Mike's work and what they looked at. So they did differentiate between, you could just sort of think of it, the thermodynamic versus the dynamic effects on changes in extreme precipitation. What he found is that it's all thermodynamic. It's all changes in the concentration of water vapor getting pulled into these atmospheric river events, and not changes in the intensity or frequency. And winds is a proxy for that. This is a result that does hold up with other work. It really does seem to be just that you're pulling more water into these events. So they're not changing in their, we don't expect winds associated with these storms to change. We expect simply the amount of water coming out of them to be greater. Another reason this work was important is in this distinction between statistical and dynamical downscaling. So for those of you that are not familiar, downscaling is the term we use to relate the coarse scale global climate model projections to the fine scale landscape level changes of climate that are needed to look at impacts. And so I'm going to show you a comparison of change in flood risk for statistical versus dynamical downscaling. Statistical is this empirical approach. One of the important limitations of statistical downscaling is that it does not capture changes in extreme precipitation. whereas dynamical downscaling does. So what you're seeing here are each dot is a river location in the Pacific Northwest, and it's the ratio of future to historical flooding. So anything above one is an increase in flood risk. Focusing in on these warm basins, they're classified relative to their winter temperature. These warm basins don't show any change because it's statistical downscaling, because it doesn't show a change in extreme precipitation. It's only reflecting the effect of declining snowpack on flood risk. These basins didn't have any snow, they won't have any in the future, there's really no effect. You could do the same model, but with dynamical downscaling using the WRF regional climate model, and you see a very different story. So if I toggle back and forth, it's not that ho-hum story from before. There are really important changes. And this, I'm focusing on the warm basins in part because these are the lowland areas where a lot of the urbanized population centers are, where a lot of the risk is in terms of people and infrastructure. So you don't get the same answer from dynamical downscaling. Statistical downscaling, dynamical downscaling is an important tool for looking at flooding as a result for our region. And so we, based on these results, worked with others to try to develop new dynamically downscaled projections. Cliff Mass is now, we worked a little bit with him, but it was primarily led by him, produced an ensemble of 12 regional climate model projections for the region. And so we've just started to distill what those results show, but that has allowed us to go beyond Mike Warner's result, which is a regionally average change, to start looking at the spatial distribution of those changes, and also at a variety of metrics that are more detailed than just the average daily precipitation. So in this case, I'm showing the 2-year event, and both for a 1-hour storm and for a 24-hour storm duration. And you can see it's still pretty pixelated. This is preliminary results. We're still working on, the relative signal, the relative magnitude of the signal versus the noise, and also methods for extracting the signal more robustly from the noise. And I'm not going to dwell on it, but we are doing some work to validate WRF. Of course, that's important. WRF is not perfect, and hopefully that's something I can talk about in another presentation sometime. But I want to move on and talk. So far I've been just talking about the climate change projections, but not about the impacts. And so I want to spend some time giving some examples of how we go from those projections to impacts. So this is one example. This is not work done by me. This is done by Alan Hamlet and Joe Hammond in the engineering department a number of years ago. But it's an example of some of the more recent work we've been doing on flooding. And what's you're seeing here is the depth and extent of the 100-year flood historically. And then they inputted changes in sea level rise and river flows to look at how that would be in mid-century and at the end of the century. And this is a big deal because before their study, all of our work had simply specified the change in the volume of water coming down the river, but not the extent or depth of flooding as a result of it. Nothing about where that extra water would go. Another example is culverts. The state is now under a court mandate to replace thousands of culverts that are currently a barrier to fish passage, in particular salmon migration. And so this is just an example. This is a prototype tool. We're currently updating it with Washington Department of Fish and Wildlife, and they're going to be putting up the updated tool on their website. But in this prototype, we're going to be trying to translate some of these to the new tool. The idea was to turn around our projections and develop them in a way that an engineer could use them for designing a culvert. So in this sort of animation, you can see an engineer entering the numbers for culvert design. And what the tool does is, in addition to showing these plots with the projections, they give a likelihood that that culvert is going to meet the regulatory standard over its design lifetime versus not. Another quick example is stormwater. So this is one where at least urban stormwater, where you can just use extreme precipitation changes directly. Those go directly into their either design standards or modeling. And we've actually created a tool. Again, this is a tool that we're updating. It's currently pretty ugly. But more importantly, we've distilled those numbers and provided them to King County, our main partner in this work. And they've actually used the WRF projections in their modeling of larger stormwater facility designs. So things like infiltration basins and detention ponds and that sort of thing, to see how much bigger they would have to be to accommodate climate change over their lifetime. So really beginning to look at the costs of adapting to climate change and what you get out of that. Okay, so those are just three examples, and I want to step back for a moment to just reflect on how many more uh, tools or resources, really how many more impacts could be addressed of this kind. And this is something that I've really started to think about as part of my work in floodplain management, showing a picture of a Puget Sound floodplain that really illustrates how, in that context, folks tend to think about the three F's: the flood, farms, and fish interests. And so there's many efforts where the stakeholder groups from each of those interests are brought together to think about how to plan and coordinate on floodplain management. And so we've been working with Pierce County to support integrating climate change into that work. And as part of that, and there's no need to read this table in detail, and in fact, the table would go down several slides if I could include it all, but it's just to illustrate the kinds of impacts and how they're distributed across those interests. So you can't see the whole table, I'm just showing a snapshot, but the rows show different really impacts or drivers of change, so changes in snowpack and low flows and so forth. And the columns show what would be impacted in each of those interests. And we were trying to really quantify both what is impacted and how you measure it. So each of those boxes contains a metric, basically. Um, and there's two things. One, there are more in here than we could possibly assess on our own. So anybody who's interested in this work, I would like to hear from you, especially if you have ideas on how to fund more work like this. But more broadly, this caused me to sort of step back and think about, there's more impacts than we could possibly address, even if there were an army of us doing this, probably. So are there different ways to think about assessing impacts, to think about planning for this, where we don't always have to do sort of go through all of the complicated um, modeling steps that I was just describing? So just to sort of conceptualize that a little bit more, bear with me. I think this is probably fairly simple for most of this audience, but it's helpful for me to think about. It was helpful for me to sort of walk through how do we go from the climate projections, warmer air and rain, to impacts. So, I'm just going to step through these quickly. There's the impacts of warming air temperatures, impacts of changes in heavy rain events, extreme precipitation, uh, and all of those combine to lead, in most cases, to bigger and more frequent floods. Right? But that is actually not the impact. That's an important consequence. It's important to quantify. I've given you some examples about how we've been doing that, but it's not the impacts, right? The impacts require taking at least one more step, and there's probably interim steps in here that I'm not showing, but to go to impacts on fish, impacts on farms, and impacts on people and property infrastructure. And sort of spelling this out like this, sort of, for me at least, really helps highlight where the big gap is. So far everything in my talk has really dealt with the upper half of this figure, everything up to the bigger floods, but not beyond so much. And so there's a real value to thinking a little bit more deeply about how do we get at these things. And I wanted to show you two examples that start to do that. First is really simple. We were doing some work recently in Icicle Creek near Leavenworth, where we were summarizing actually existing stream flow projections for them to use in their water supply planning effort. So this is what those stream flow projections show in terms of the percent changes for each month for the 2080s, end of the century. And I wanted to sort of look at that in terms of looking at the past as an analog for the future. So I did the same thing, except I didn't use any modeling. This plot here is just observations, and it's just comparing the year 2015, which is anomalously warm, to the stream flows in the year 2015 to all the other years in the historical record. And if you do that, you get a different picture from the 20s, but a very similar one, especially if you look at the two black lines, the average lines. And so that's just an illustration of how the year 2015 really could be a good way to sort of to look at what the impacts might be when this becomes more routine in the future. And the advantage of looking backwards is that we don't have to model that link between changes in stream flow to impacts. We actually can, it's observable, right? It can be documented. So I think there's a lot of potential to expand on this and do it a little more deeply. And we haven't done that, but I'm interested in it. Um, the other example is to, I'm going to skip that slide. The other example is to do sensitivity testing. So this is an example, we actually spoke with the consultants early on in this project. And basically what they had done with the City of Portland is looked at a whole bunch of climate projections, realized they were complicated to interpret, to ingest. There's a lot to decide about which ones to use. And it was beyond their expertise and their capacity to deal with. And instead, they said, well, we've got a good understanding of our stormwater system. We really understand our stormwater model and how it works. Let's just perturb it and see what happens. So instead of pulling in climate projections, they just did sensitivity testing. They upped the intensity of their design storm, and they upped the volume of their design storm. And they looked at what happened. And for example, they found that intensity is much more important than volume. But they also were able to look at hotspots and places where they could really get a good bang for their buck. And you can map the climate projections onto this. And even as they're updated, you can continue to map them onto this as they change over time. So this is sort of a good starting point for doing a more of a bottom-up analysis of climate change effects. Okay, but I want to go one step further. So far, so we talked about climate projections and then we talked about impacts. So far, apart from the last slide, we've just been talking about exposure to climate change. And that's just one component of vulnerability. So vulnerability is typically conceptualized as a combination of exposure, sensitivity, and capacity, adaptive capacity. So I showed you one example of assessing the sensitivity, and that could go much more broad to many other things, right? But it's this sort of bottom-up look at how much impacts there are in response to a certain amount of change. But more importantly, adaptive capacity. So this is another thing that came up in doing my work with Pierce County, and in this case, a really clear gap in our work. We're trying to prioritize research related to climate change that can support floodplain management. And I realized in that project that we were really focusing on the exposure side, a little bit of work on sensitivity, but we really hadn't thought deeply anyway about adaptive capacity. And what do I mean by this? I think this is things like, how this could be anything from social, economic resources to cultural barriers to action, institutional, regulatory, all of those things that go into how and what is the capacity to respond. And I bring this up also, given the theme of the Summer Institute, because this is where a lot of the equity considerations come in. So just to illustrate that, one example, as part of the Pierce County work, we've been looking at the Clear Creek Basin, which is in this bottom right of the image. Just to orient you, this is Tacoma and the Port of Tacoma. So this is a really valuable basin. It's nestled in the heart of a highly developed watershed. It's in the lower watershed. I-5 is actually just beyond the outlet of the creek. It's got really important salmon rearing, side channel rearing habitat, a lot of small farms in a county that doesn't really have small farms in general, and a lot of low-income housing because it is in the floodplain. It's behind an unaccredited levee. And so there's been a lot of focus on this and how to manage flooding currently in particular, but as well as in the future in this area. And just a really quick example about blind spots and the importance of thinking about equity, it was 3 years at least into this process the county is convening that they realized that actually the residents of the mobile home park had not been included in any of the discussions yet, and were actually going to be pretty central to the impacts of some of the interventions they were discussing. So that's just one anecdote, but one of the sort of lessons that we learned along the way. More broadly, in order to make a beginning to addressing this big gap in terms of adaptive capacity in my work on floodplains, I went to learn from others, and I looked at this recent report, Social Science for the Salish Sea, developed for looking at Puget Sound ecosystem recovery. It's a research agenda, but I then, that's meant for ecosystem recovery. I adapted it to look at floodplains and climate change in Pierce County, and that went into our plan for research that we developed in collaboration with Pierce County, and actually we sort of categorize them. It includes technical studies as well as ones that would address adaptive capacity and sensitivity. And we're actually moving forward with a lot of those projects now, that the group has prioritized. And I bring this up mostly because this is an area where I'm still, especially adaptive capacity and how to really better incorporate these other aspects of climate modeling into our work. And I'm really just starting to learn about it. I would love to hear from any of you that have ideas or suggestions. It's kind of a good time because we're now expanding the Pierce County work to Snohomish and Whatcom counties in the next few months. So I'll stop there with just one final thought. One of the things we often say to ourselves in the climate impacts group is that we want our work to be not just useful, but quote unquote used by. So that's what we've been trying to do in this work, sort of tried to illustrate. And I'm looking forward to the discussion after this talk. Thanks.